Now let's see the principle of inclusion and exclusion, also called as PIE, which is a very important principle in the study of combinatorics. Let us take a simple example first, and we will generalize the principle after that. Let's consider that there are say three sets denoted by A1, A2 and A3. So we draw a general Venn diagram to represent these three sets. So we have A1, A2 and A3. And suppose we are interested to know how many elements are there in the union of all these three sets. So that is n of A1 union A2 union A3. Now, by a crude approximation, we may first add up all the elements in the individual sets, that is n of A1 plus n of A2 plus n of A3. Now in this process, we have actually double counted the areas which are common to the pairs of the two sets each out of the given three sets. So that is nothing but, if we consider this particular area which is common to the sets A1 and A2, this is getting counted twice because it is coming in A1 as well as A2. So therefore we must subtract it once. That is, we must subtract n of A1 intersection A2, and similarly we must subtract the other two possible areas also, that is A2 intersection A3 as well as the area of A1 intersection. Now in this process, what has basically happened is, although the areas which are common to the two sets each have been accounted for, the area which was common to all of the three sets, that is this particular area which is the common region of all the three sets A1, A2 and A3, this was present in the individual numbers, that is A1, A2 and A3, as well as it was also present in the remaining three terms which we subtracted. So that means effectively we have not yet accounted for this particular shaded region which is common to all the three sets. So therefore now we must bring back that particular count by adding n of A1 intersection A2 intersection A3. So now that completes the entire counting, and this is how we use the principle of inclusion exclusion, by alternately including and excluding the different possible overlap areas. Now we can generalize this principle, that is not only three sets but can be extended to any number of sets or events. So therefore we can write the generalization now. So if you want to know what is the number of elements in the union of certain group of sets denoted by AI, where I can vary from 1 to n, is given by, now if we see the first particular group, that is we are adding up the number of elements of the individual sets first. So that is nothing but the summation of n of say AI, where I varies from 1 to n. Now from this we have to subtract the number of elements which are common to two sets each. So that means is the minus summation of n of AI intersection say AJ, where of course I cannot be equal to j because it's basically has to be the two different sets. Now lastly, here if we see that we are adding back the number of elements of intersections of three sets, so therefore here we will have the addition of summation of n of AI intersection AJ intersection AK, where I is not equal to j and which is not equal to k. So I, j, k, all three must be different from j. and so on, till we go to the last intersection, that is the intersection of all the sets together. So that is how the principle of inclusion exclusion is to be used.